Good morning, friends. I should say welcome back because we had a gap of about 2 to 3 classes, right? So to compensate that, you will have today's session and as well as next one more session. Continuously you will get instead of 3 sessions, you may get 4 or 5 sessions this week. Probably 4, and if possible, the 5th class also. This is for this week. I would like to do it. Now remember, our topic was Gauss law, and we have used Gauss law in finding intensity of electric field for 2 systems like line of charge we did, right? And then also we did for the case of sheet of charge. The cases of 1 dimension and 2 dimension distribution of charge. Now today let us take up one more case. This will be a 3-dimensional distribution. Again, the case of application of Gauss law finding intensity. Now the case is, you can look here, this is spherical charged conducting shell. The same can also be spherical charged conducting sphere also. Shell means inside hollow, right? Sphere means inside also stuffed with material. Now, whatever results that we now arrive will be the same for 2 cases. What is that? Either spherical charged conducting shell or even the case of spherical charged conducting sphere also. Results are the same. Why, you tell me? Because we know that whenever a conductor is charged, all the charge resides only on the surface, the expression property. Therefore, if it is a shell and we charge it, the charge is present only on this surface. This is the case of shell. Is it not? Now, even if it is the case of a sphere, suppose this is a conducting sphere, inside stuff is there. Now, this time also when the conductor is charged, the sphere is charged, net charge inside the conductor is always 0 because of the expansion property. Thereby all the charges are now appearing only on the surface, right? Therefore either case will be the same, right? Now we take this is a conducting sphere or shell of radius. I write this radius as a capital R. The symbols, always I keep telling you, no confusion with symbols. Be very clear about which symbol, use it for which parameter. Capital R, radius of this shell or conducting sphere, and it is charged. And here I show again a charge, a positive charge of capital Q, which is present only on the surface. Which is present only on the surface, right? This is what is the charge that appears on the surface, and this charge I take it as capital Q. Suppose the charge on the conducting sphere, the shell or anything one and the same, right? Now we want to find the intensity due to this shell or conducting sphere at different locations. At different locations means what happens in the case of a point well inside the surface. Well inside the surface, that is what is inside point. What is the intensity? And if suppose if I consider any point on the surface of the sphere or the shell, what will be the intensity? And similarly, what will be the field outside the shell or the conducting sphere is the question. So we do it in step process. First we do it for inside, then we proceed with the further. In all the cases, you remember we have the 3-step process. What is that? First, once you got the point of observation, construct a Gaussian surface passing through the point of observation, right? Constructing Gaussian surface, that Gaussian surface should pass through point of observation. And then second step, yes, apply Gauss law for dividing into elements and Gaussian surface. Apply Gauss law for one element. Third law, evaluating the integral, right? You remember we did it for the last 2 cases. That is what earlier I have told you. 2 1 2, 3 1 ja 3. Now the question is 4 1 ja, that is what is your job now. Now you see capital Q are the symbols. Now supposing I consider a point. I call this point P1, which is present inside the surface. Now point is to find the intensity at this point. Yes, the process is constructing Gaussian surface, and most of the cases we always take the case of symmetry. And remember, all these geometries are not 2D but rather they are all 3D. It looks a circle for you. Remember, this is not a circle, this is what we said a sphere, right? Therefore, even the Gaussian surfaces that we construct, they are all 3D geometries, not 2D geometries. Therefore, now P1 is the point at which we need to find the intensity. So this is what is P1. For that, what we do is that now, which is at a distance, suppose I call this small r, or better I write it some symbol, I write it as a d. So d is the distance of inside point from the center of this sphere, which I am taking as O, right? Now here you see, to find intensity at P1, now we imagine a sphere of radius d. To find the intensity at the point P1, which is at a distance d from the center of our sphere or shell, right? What we did is, yes, this is what is the Gaussian surface that now we are constructing. This is the Gaussian surface, is a sphere of radius d, right? Now let us see what is the case of this Gaussian surface and charges. Therefore, now I am writing at P1. Yes, Gaussian surface is, yes, tell me what is that? Yes, is a sphere of radius small d. Inside you can write d less than capital R, right? Inside point, therefore d less than capital R. Now immediately we can see that this Gaussian surface, look, all the charges are present on the surface of the sphere or the shell. Therefore, inside this Gaussian surface, no net charge is present, is it not? Because expulsion property of the charge, inside this conducting sphere or for the shell, no charge is present, is it not? So that is what is the point that we mentioned, and immediately we will have the result, right? So what is that statement we are doing? This Gaussian surface does not enclose any net charge. Why? Because you can add that. Because of expulsion property, all the charges are present on the surface. Therefore, now when we are writing this integral E bar dot ds bar is equal to q by epsilon naught, this integral, this is, yes, the same sigma qi. This sigma qi is 0, therefore E is 0. Now this is equal to 0. Because no charge inside this Gaussian surface, and therefore all this expression will give us one result. Therefore, this will yield our result as E at P1, which is nothing but E. I am writing I for inside. Okay, EI is equal to 0. No field is present inside the shell, charged shell or charged conducting sphere. EI is equal to 0, D less than R, right? At any inside point, the field is 0. Now the point comes. The same, let us continue further. We shall consider another point, say P2 on the surface. Let us see what will be the result, right? So if you are done with this, I will go for the next one. Remember in your examination also, you please do write 3 figures separately. Now this is the one which I have represented for inside point. Now when I am discussing the case of a point on the surface, I will redraw this figure, right? Don't use the same figure for all the cases. It's only a case of 5 seconds, right? You draw the figure separately. Now this time, one more time, I remove this P1 point and the Gaussian surface which I have shown inside a sphere of radius small d and all. Now I will take a point which is a point, look at this, right? Is that okay? P2 is a point present exactly on the surface of the shell or a charge conducting sphere. You remember I have mentioned one important thing regarding discrete charges and the distribution of charges, continuous distribution of charges. There I have mentioned that at this side of the discrete charges, field is never defined, whereas in the case of continuous charge distribution, look, this point P2 is present where the charges are there, but still field is there. Now this is because of the internal structure and all. So now here P2 is a point at which I want to find P2. At point P2. And what is the point P2? I mentioned on the surface. It is present exactly on the surface. Now, one more time Gaussian surface. Now see here, earlier it was a point P1 at distance D from the center D less than capital R we said. Now this time when point P2 is present exactly on the surface, now the Gaussian surface is nothing but surface of that shell itself behaves as a Gaussian surface. Is it not? Because we need to always construct a Gaussian surface passing to a point of observation and we are using symmetry. Therefore here we write Gaussian surface is, yes, Gaussian surface is the surface of, yes, surface of a charged shell itself. Charged shell itself. That is the point. Okay. See here. Gaussian surface we have constructed, and this Gaussian surface is nothing but now the sphere of radius capital R, therefore that is nothing but surface of the shell itself. Therefore now what we do is, yes, the same case, dividing the surface into large number of small elements and consider one element and write this, the same goes. Therefore now what we do is, supposing here we take one small element, let me show it with a different color for your good observation. This is what is an element which I am representing with this red color, right? I think it is legible. Red color, this is what is the element on the surface. If this is what is the spherical surface, I have considered one small such element of surface, and of course ds bar always normal to surface. Therefore here I will say, yes, normal to the surface, one red color vector you can find here. This is what is d, yes, bar, ds bar. And also by principle, whenever electric field lines we consider, the field lines either enter or leave always normal to the surface. Therefore here I show this another vector E bar with the green vector. Now this is what is another vector. Guys, please see these vectors in different colors. I am writing this vector is E bar. Now both E bar and ds bar are normal to the surface, ds bar normal to surface, E bar normal to surface. What does it mean? E bar and S bar, ds bar. These two vectors are parallel, right? Now this is what we do. Now the Gaussian surface is divided into large number of small elements, each of S ds bar. Since here it is a uniform curvature, not what we get, therefore each element is identical. The only thing is that normal keeps changing from element to element. So this is what is element, each of area ds, magnitude I am writing, ds magnitude, each of ds. Now here we mention at ds bar, E bar is always, or let us write like this, at any element, right? At any element of area. What was the result we said? ds bar is parallel to E bar, or E bar parallel to ds bar, and that is why I have told you, show the figures separately for the inside point, outside points or surface points. ds bar parallel to E bar, that is theta is 0 degrees. Therefore, using Gauss law, still correct? Using Gauss's law, yes, integral E ds cos 0 degrees. E ds cos 0 degrees is equal to, now you see, as earlier I have told you, all the charge resides only on the surface, and now the surface itself is the Gaussian surface. Therefore, what is the charge enclosed? Capital Q is the charge. Is it not? So capital Q by epsilon naught. You please make a mention. Capital Q is the total charge on the shell. This is what is the charge given to the shell. Q is the total charge on the shell, right? Now immediately our next step, we have our result. What is that? What is that? Shall I write here? Yes. Now this is integral E. I am taking outside the operation. Integral D, yes, cos 0. 1 I have taken, right? This is Q by epsilon naught. This integral ds is nothing but, yes, integral ds is, yes, nothing but surface area of sphere. Because ds is one element of surface of the sphere we have taken. Therefore, this integral ds is surface area of the sphere. Again, what is the surface area of the sphere? If r is the radius of the sphere, 4 pi r square. Remember? Therefore, now we have E times 4 pi r square is Q upon epsilon naught. So, final answer, final expression for capital E. Therefore, this capital E is equal to 4 pi epsilon naught. Therefore, I write it as 1 upon 4 pi epsilon naught. This Q is there and r square term. Therefore, this is Q by r square. Of course, we got the expression. Now, the most important thing, understanding and or analyzing that expression. Right? Let us see that. I have to change the board. Now, let us see that also. Yeah. Now, shall we understand the results? The result is that E field on the surface at any point on the surface, ES is that 1 by 4 pi epsilon naught K, 1 by 4 pi epsilon naught, 9 into 10 minus 9 times Q by R square was our result. Now remember, just recollect the first expression that we have defined for intensity of electric field was for a point charge. If Q is a point charge at a distance capital R or small r, whatever the symbol, what was the expression you got, remember? Yes? For a point charge Q at a distance R, we have said KQ by R square. Now look at this. ES is equal to, again the same expression you got, KQ by R square. So what does it mean? It means that though all the charge is present or all the charge is distributed on the surface, now this shell or the conducting charged sphere, it is acting as a point charge, as if all the charge is present at the center. This is not valid for inside point. So for any point, right, on the surface or beyond the surface, charged sphere or charged conducting sphere or charged shell, they are acting as a point charge, as if all the charge is present or concentrated at its center. It's a very interesting result that we found. Charge is distributed, but when it comes to the question of behavior, it is acting as a point charge. Of course, this behavior is not applicable for a point inside the shell or conducting sphere, we said, right? Therefore, now this is one important and one more thing, this is always, of course, vector. Therefore, I keep telling you, please mention the direction. It is always, yes, normal to surface. Normal to surface. One more important thing is that earlier you remember when we have discussed the case of this same charge distribution and all, charge by surface area was called a surface charge density. Can you find that here? This numerator term is Q. 4 pi capital R square becomes the surface area for the sphere. Therefore, this Q, denominator 4 pi R square, this term becomes sigma. See what I am writing? This is Q by 4 pi R square times 1 by epsilon naught. Is that okay? Right? Then all this expression is nothing but sigma. Therefore, this ES is equal to, now relating two things. When I am relating things, I am telling you it is not something new. Say formula number 2, formula number 10, don't make it like that. You see for yourself and do it. ES is equal to surface charge density upon epsilon naught. Say one more result, very, very useful. What here you find is that ES proportional to sigma. Field ratio, I will always take it as the ratio of surface charge densities here. E proportional to sigma is the result for, we are telling this case of charged shell or conducting sphere and what. Few things I want to discuss a bit further, but now because it is because of a limitation of time, I just leave at this point. And I would like to proceed further. Now we did the case of a point inside the surface and on the surface. The two results were very interesting. At all inside points, no field is present. E is absolutely zero. Now it is present on the surface in a finite value. Now the case of outside point, right? Now the case of outside point. Again, you write it as figure number 3 also, right? Because as I have told you, the same figure does not do for all the cases, right? So whichever case you are discussing a particular figure, you please draw that. Now I remove this P2 point and all, right? This P2 point all removed, all these vectors and elements removed, right? Now I consider a point. I write it as P3, which is at a distance, suppose small r. Now look here, this small r distance I am taking from the center of the sphere, right, shell or sphere. The point is sometimes you may also be given distance of the point from the surface. In such case, suppose if this is what is some x from the surface, then small r becomes capital R plus x. So those kind of small changes you need to be very careful when you do any other examples. So symbols, whenever you are using symbol with complete correct meaning, is very, very important. I don't know how many number of times I have just keep on repeating this particular statement, right? When I am doing with such a repetition, you please understand the significance. In your practice, this is a very essential thing. Smaller is the distance of point P3 from the center. Again, to find intensity at P3, the same case again. What we do here? Here I show a Gaussian surface, this time with red color. So this is a Gaussian surface. A Gaussian surface which is a sphere of radius small r. Radius small r, please do remember from the center, right? This is a Gaussian surface which is a sphere of radius small r. Now this is where at P3 I am writing. P3 means, yes, outside point. P3 is outside point, right? Now first to begin with, P3 is, yes, at a distance small r. Do remember, greater than capital R. Small r greater than capital R. P3 is at a distance r. Of course understood from the center. Now to find, again the same statements, to find intensity at P3, yes, we imagine Gaussian surface, yes, passing through point P3, passing through the point P3, and which is yes, a sphere of radius small r, a sphere of radius small r, and encloses. When you take that bigger sphere of radius small r, then what happens? All the charge will be enclosed by the Gaussian surface, and it encloses, yes, is it not? It encloses total charge on the shell. Total charge on the shell. Encloses total charge on the shell. I have told you many times from the first PU, you have to improve your expression. Simply learning PCM or PCB or this and that. See, when you have come to the stage of PU, 12th class, the important asset for you is your expression, either in writing or verbally. Do please, it's been a high time, don't use Xerox books, don't use guides, make a notes of your own, go to the teacher. If you want to improve that, or if you want to have any clarity about that, you go to the teacher, show them, but make a note of your own all the time. Now here what you find, Gaussian surface. So in our next step, what we do is that apply Gauss law and find the intensity. And of course, even I can leave you at this stage because this is your job now. In fact, your duty to do it, right? Therefore now, one more time, this time let me take Gaussian surface, right? So this is what is a Gaussian surface, a green color element that I have shown here. Again, one more time, this normal representing ds bar, and again the same principle applies here also. Electric field intensity, a vector parallel to ds bar, right? This is what is the vector E bar. So the same lines goes here also. What is that? At any element or at any element of area, ds bar parallel to E bar. In fact, the other way is correct representation. E bar parallel to ds bar, theta is again 0 degrees, the same two lines to get your result. And of course, yes, already you got this result as well, right? What is that? Therefore, applying Gauss law, integral E ds cos 0 degrees is nothing but now q by epsilon naught. Again, this q refers to C here, that is why we have made a mention and underline that point. Because this Gaussian surface encloses the total charge on the shell, therefore I have taken this as capital Q by epsilon naught. The same goes here also. E times integral ds is equal to q by epsilon naught. This E for outside point. This integral ds, again the same surface area, which is 4 pi r square. This time that r refers to this smaller because it is the biggest here that is under consideration. Therefore, this is E times 4 pi r square is q by epsilon naught, and therefore now I have my final result for this intensity. What is that? Right? Therefore now E at any outside point, is again the same 1 by 4 pi epsilon naught q by, see what is this, small r square, or from the center. Again it looks the same form as that for the point charge, you remember, and that is why we have told this is behavior when it comes to the point on the surface outside point. This is what is the expression. Even this expression also, what you can do is you can have a small change. How? This earlier we have shown, this is 1 q by 4 pi epsilon naught, q by 4 pi r square, let me write it as. So this is r square in the denominator that I have used, therefore here I will use r square by small r square. Is that okay? R square, right? Therefore this expression E at any outside point, you will write it as sigma times capital R by small r whole square. Now the point is, we have all the three results. Inside point the field is 0, outside point we have given expression, and remember surface point also we have given. When you look at all these three expressions, one thing is clear. So what is that thing that you can make it out? Here small r is greater than capital R, remember. Therefore this EO is less than ES is a common sense thing that we have shown. EO is less than ES. Now the point is, when ES is greater than EO, the point comes that ES is maximum. In the case of a charged shell or a charged conducting sphere, surface intensity is maximum. Is it not? So that is also one more important thing that you can write as a note, note 1, note 2, note 3 when you write. So now I am writing some important note points. Again, please do remember, it is again, the direction is normal to surface. It's a radially away or radially towards, depending upon the charge. Because every time I am showing you the positive charges, therefore the vectors are there. If it is the negative charge, of course you know the direction is just the reverse. So it is normal to surface. Normal to surface. Now if I have to write some important note points, right? What are those note points? See, when you are doing this in the examination, don't forget, if asked for a definite point, find intensity on the surface, then only one figure will be sufficient. Supposing if you ask for two different cases like inside point, surface point, something like that, then you do those Gauss law applications separately with a separate figure. Right, now here comes note 1. In the case of yes, conducting in the case of charged shell or conducting sphere, This is the case that we are discussing anyway, right? Why I need to mention that? In this case, the first point to be remembered that E maximum is ES. E maximum value is on the surface. And this is what we have taken as yes, KQ by capital R square. If it is capital R, small a, small d, doesn't matter, that refers to radius, right? And number one more thing is very interesting that what we observe is, let us show a graph, because every time understanding the results in terms of graph will be very helpful for you. Not just I am telling you NEET examinations or the examinations you will get, no, not like that, you leave that apart. Our learning is never for examination. Our learning is always for our upliftment of our habits, our way of thinking, what not anything. It is self-elevation. A graphical representation always improvises the concept or the subject that you have. It will give you more and it will throw more light on it, and your understanding becomes better. This is where I am showing you one such a graph. Suppose this is what is the graph I have taken. Alright, this is small r, this is small r. What is small r? Distance of the point of observation from the center, Okay, supposing if I am writing it as small r, this is the graph which I am showing it for this given situation. What is the situation we have been telling? Yes, this is a sphere, this is a radius capital R, and this is what is the charge, positive or negative, right? Yeah, now let me show the symbol. This is what is capital R, the radius, this is the center, Now this is what is the, we are discussing, this is what is R1, this is what is R2, this is what is R3, like that. Okay, now R refers to distance from the center, and on the y-axis I am taking, yes, on the y-axis I will consider the intensity. So intensity versus the distance from the center. R versus capital E. Now this is what is R is equal to 0, which means center of the particular shell. And now this is what is small r is equal to capital R, which is a point on the surface. And afterwards whatever you get will be the outside point, right? This is how you represent each and everything and understand meticulously. What is small r? Radius. Radius means if the point on the surface, any distance after the small r will represent outside point, like that. Now you see that from r is equal to 0, r equal to capital R, that is, it becomes inside point. This all shows the inside point, right? This is what is the center. Now here to here, this is what is inside. Exactly at this point, this refers to surface, and afterward this all represents outside point, right? Now here, any inside point we have shown EI is 0, right? Therefore no field till this small r equal to capital R. This is completely no graph because E is 0. Now we know that on the surface it is maximum, therefore this is what is E on the surface, and this is what is maximum. And after that, for any point, what is the result that you got? You see here E proportional to 1 by R square. E proportional to 1 by R square is the result. E proportional to 1 by R square. Is it not? It's not a first degree equation. Therefore, we will get a curve. And since this is an inverse relation, you will get negative slope. So it should be a curve with negative slope. That is what we represent here. Therefore, curve with negative slope, and that slope should gradually decrease. So this is what you get. This is the curve. See, this is a curve with negative slope, right? Remember, this is also a curve with a negative slope. But what is the difference here? Here the slope is gradually increasing slope, right? But here it is not the case. Therefore, it is gradually decreasing slope. Therefore, this is what is the graph that we get. So this is what is the graph, and of course you can also show it like from this is center, all the distances now towards your right and towards your left even that you can also show. So supposing the same graph, if I want to represent, because we have here from the center on either side, therefore better representation, if you want, this is the better representation. This is small r, right? And this is what is capital E. This is what is capital E, and this is r equal to 0. On either side, now this is what is r is plus r, and this is what is r is equal to minus r, the surface points on either side. Now both this one and this part refers to inside point, no field, therefore from this point to this point it is no curve, discontinuous we get. Therefore here of course it is a curve with negative slope, here also curve with negative slope, and this is what is the maximum referring to E maximum on the surface. And from r equal to minus r to r equal to plus r, the graph is like discontinuous like this. So remember, when we told Gauss law is a three-step process. The same we did for all the cases. Now if you want me to do that, we'll do one or two extra cases as well. Let us see that.